In this video, I'm going to introduce a subject called interpolation, which may seem similar to curve fitting. Both approaches attempt to determine the behavior of a set of data between measured data points, but their fundamental approach is very different. In curve fitting, the estimate did not match all the data points. In interpolation, our estimate will match the data exactly at the data points. As I said, the goal of interpolation is similar to curve fitting. In both approaches, we're given a set of data points and we want to infer the behavior of the relationship between the data points. However, the fundamental approaches used by the two methods are very different. In curve fitting, we assumed that the given data was the result of an experimental measurement which contained noise, measurement errors, and other uncertainties. The goal was to determine an underlying functional relationship that best described the trend of the overall set of data. Interpolation has a different attitude towards the data. First, we don't necessarily need a functional relationship that describes the overall data set. Second, the approach assumes that the data points we're given are exactly correct. So, any interpolation approach will match the values at the given data points exactly. Curve fitting techniques can be used to interpolate data. If you use n data points to fit a polynomial of order n-1, the polynomial will pass through all of the n data points. This example uses 11 data points. If I fit a 10th order curve to the data, it looks like this. However, with higher order polynomials, there tend to be a lot of wiggles in the curve that probably don't reflect the actual behavior of the process. To get a similar result, but with lower order polynomials, we can divide the data up into a series of little chunks and then curve fit a lower order polynomial over each little chunk of data. The process of using lower order polynomials to describe sections of the data is called piecewise curve fitting. For example, suppose we have this set of data and we want to perform piecewise curve fitting. We still choose an arbitrary order polynomial to represent the data. Then we'll use an appropriate number of data points to fit that polynomial to a local region of the data. For example, the simplest approach is probably just to connect the data points with straight lines. Two data points uniquely define a straight line, so you can use the equation of that line to estimate a value for the function between the points. This approach is arguably the most common interpolation approach. It's reasonably accurate and incredibly simple. To use a quadratic function to interpolate, use 3 points in the subinterval to determine the 3 coefficients in a quadratic equation. For this data, we might get something that looks like this. Notice that in both of these approaches, the curve isn't smooth. We always end up with these kinks in the curve fit between subintervals. Next, I'll talk about a couple of approaches that allow you to create a smoother curve connecting the data points. Using cubic polynomials to interpolate is probably the second most popular approach. This is the general equation for a cubic polynomial. There are 4 unknown coefficients in this equation. We could fit the equation using 4 data points. However, it's more common to use other conditions to create a smoother curve. For example, you could create 2 of the necessary equations from the values of the functions at 2 adjacent points. The remaining equations can be created by applying conditions that make the slopes of the cubic polynomials continuous where they join together. There are several variations on this theme. 2 of the most common are what is called cubic spline interpolation and piecewise cubic Hermitian interpolation. Here's a set of data to which we want to fit an interpolating curve. This is what a cubic spline interpolation of the data will look like. The curve passes through all the data points, it looks fairly smooth, and it doesn't have the large wiggles that a high-order polynomial will produce. All in all, it's an aesthetically pleasing representation of the data. However, it is considerably more computationally intensive than a simple piecewise linear curve fit. Now I'll discuss some of the tools available in MATLAB for curve fitting. There are 3 main functions: interp1, 2, and 3. They do 1, 2, and 3-dimensional curve fitting, respectively. All the examples in this video have been one-dimensional, so there's a single independent variable. Two-dimensional and three-dimensional curve fitting have 2 and 3 independent variables, respectively. Example syntax for one-dimensional curve fitting shown here. The input arguments are vectors containing the x and y data points, and a vector, xi, that contains the values of x where the interpolated values will be determined. The final argument, method, defines an interpolation approach. The output argument is the interpolated values of y at the corresponding values in xi. These commands support a variety of interpolation approaches. Nearest uses the y value at the closest value of x to determine the interpolated value. Next and previous use the y value to the immediate right or left of the interpolated value. Linear performs piecewise linear interpolation. P-chip does piecewise cubic Hermitian interpolation, and Spline performs cubic spline interpolation. There are a couple of other options, but these will give us enough different approaches to do some demonstrations with. First, I'll create some data to use when I do some interpolations. The function I'll use is y equals x squared plus 3 times e to the negative 3x. I'll evaluate the function at increments of 0.4 between x equals 0 and 2. Then calculate the corresponding values for y. And finally, I'll create an array of values where we want to interpolate the function. I'll interpolate the function over the range of 0 to 2 at increments of 0.01. The values where I'll interpolate the function will be in an array named xi. For later reference, I'll calculate the actual values of the function at these points and put them in an array named y_exact. Now let's see how interpolation works with the nearest, next, and previous options. First, I'll use nearest. The data points are the red circles and the interpolated values are the black line. The interpolation simply takes the value of the data point that it's closest to. I'll compare that to the next option. To compare the two approaches, first I'll hold the current figure. Then I'll use the next option to create the interpolated values. Now the interpolated points take on the value of the data point to their immediate right. Let's also use another very simple interpolation function, linear interpolation between adjacent points. Now the interpolated values just consist of connecting the dots with straight line segments. This is the approach that MATLAB uses in its plot function. So if I create a new figure and type plot x comma y, I get the same figure as when I used linear interpolation. Before I do spline and cubic Hermitian interpolation, I'll clean things up by closing the current figure windows. I can do this with the close command. Now let's use spline and cubic Hermitian interpolation on this same set of data. In this case, the differences between the two interpolation approaches is subtle, so I'm going to plot the exact function values as well. MATLAB does complain a bit, since there's a new function called P-chip that also performs cubic Hermitian interpolation, which will be replacing the cubic method. I'm used to using cubic, so I won't be switching over to the new function until the last minute. For this case, both methods look like pretty good approximations to the data, but it does look like the spline method is closer to the exact solution. The green dashed line is the exact solution, the black dotted line is the spline solution, and the solid blue line is the cubic Hermitian interpolation. Which interpolation approach is a best fit to the data depends on the data set. In the last example, the spline gave what seemed to be a better interpolation scheme than the cubic Hermitian approach. But let's take a look at a different data set. The data set I'm going to use is in these vectors. To visualize the data, I'll plot it. The data are at three discrete values, -1, 0, and +1. Now I'll set up a vector of interpolation points, which are, of course, much more closely spaced than the data, so that we can see the behavior of the interpolated function between points. Now let's compare the spline and cubic interpolations on this set of data. In this case, the cubic Hermitian approach seems to give a slightly better solution. The spline approach contains some oscillations that aren't really indicated by the data itself. Finally, let's do a linear fit to the data. I want to add this to the existing plot, so I'll hold this plot. Now I can add a linear interpolation to the plot with these commands. The linear interpolation, the green line, seems to be a good approximation to the data as well, and it's computationally much easier than either of the other two approaches. Finally, I'll revisit something that we did as a curve fitting example. As I pointed out in the curve fitting chapter, if I fit an n-1th polynomial to n data points, the polynomial will pass through all the data points. This counts as an interpolation approach, as well as a curve fitting approach. In the data set we're working with here, we have 9 data points, so I'll fit an 8th order polynomial to the data and plot it as a dashed magenta line. As before, we get a lot of big wiggles in the curve fit. Using a high order polynomial to interpolate data is generally a bad idea. The main thing to keep in mind about interpolation and curve fitting is their fundamentally different attitudes about the role of the data. To get the best of both worlds, sometimes the methods are combined. As an example, computer models of power plants, rocket engines, and so on require lots of fluid properties which provide temperatures, pressures, enthalpies, and so on as functions of one another. The curves describing these relationships are usually generated from curve fits of measured data. Unfortunately, the governing equations are pretty complicated, and calculating them thousands and thousands of times for a simulation is very time-consuming. So, the governing equations are used to generate tables of data, and the simulation interpolates from those tables to efficiently get the necessary fluid properties.